the hour, so why don't we go ahead and get started. I'm glad to see everyone who's joined us. Welcome. Because of the number of people that we have, what we generally do is put people on mute, and then if you have questions, there's a chat window that you can use to ask questions, and please do that. And then Anne, who's helping to host this, will keep track of those, and then when we get to the end, we'll be able to answer those questions, which is certainly what we're interested in. So my name is Jeremy Gregory, and I'm the Executive Director of the Concrete Sustainability Hub and one of the research principal investigators. And during these webinars, we've been talking about different research that we have and have talked a few times about pavements. Now we're going to talk about some of our buildings-related research. And in particular, our topic here is related to hazard resistance. And when I talk about hazards, what I mean is, hazards usually from related to natural disasters. And this is obviously a really big topic, particularly in our country, where we have a lot of property damage. And over the past couple decades, it's been, in the hundreds of billions of dollars due to a variety of different hazards. And what's interesting is looking at the way that we as a society, or as our government tends to think about hazard mitigation. And by that I mean, efforts we can take to avoid that. What this chart is showing here is basically investments by FEMA, the Federal Emergency Management Agency, for what they call pre-disaster mitigation grant spending, because FEMA does award grants that they call disaster mitigation, but that's actually usually only investments that are made after a disaster occurs, basically to help with rebuilding. So this would be more, this type of investments that we can see here are more related to investments you would do up front before a disaster occurs. And the blue line here goes with this axis right here, and it's the annual amount of grants that they give out over the past 10 years or so, and it's in millions of dollars, right? So it sounds like, spending whatever, $100 million per year is approximately kind of what it's leveled out as. Sounds like a lot, but look at the orange line here corresponds with this axis right here. And you can see that generally that pre-disaster mitigation grant spending has been, a very, very small fraction of the total amounts of FEMA-related grants. So clearly what this is saying is that we're prioritizing response to disasters over mitigation of disasters. So we compare this, basically, these numbers right here, the hundreds of million dollars to the $7.2 billion spent on average on annual recovery assistance, right? So that's where we've prioritized things. Now, one of the things that I want to talk about here is what we mean by resilience. And generally, you see a lot of different definitions of it. A pretty simple one for me is it's a system's response to a problem, right? And we can characterize the performance of a system, and that can be anything from a telecommunication system or an electrical system, or in this case, we'll be talking about a building, and it has some type of performance over time. And as we go over time, eventually we have a hazard that occurs that leads to a drop in performance. And that drop is generally what we refer to as hazard resistance, right? The amount that it can withstand that drop in performance. There's also an element that has to do with recovery over time, and depending on what kind of resilience you have in place and what kind of efforts you have after the disaster, you can either have a system that never recovers to its same level that it was pre-disaster, and I'm sure there are people in the lower Ninth Ward of New Orleans who would say that they're on this red path or somewhere there. Ideally, what you'd like is to be able to get back to the same level of performance you have, or even better, get to a better level of performance. But that's basically what we mean when we talk about resilience. Now, mitigation is a way of improving a building's resistance to a hazard. And so there are a bunch of different ways that you can do this. One is to use elevated structures and utilities. So you see this in a lot of flood-prone areas where, most of the, in this case for a residential structure, the living quarters are on the second and third floor, and in the first floors, the garage, they make sure utilities are up high. So, that's one thing you can do. Use of storm shutters is very common as a way to prevent the impacts of pressure differentials when it comes to hurricanes. Safe rooms are often used in tornado-prone areas. And the way that you design the shape of the roof and then also the connections can also improve hazard resistance, okay? So we know that all of those things exist, but what a big motivation for us in our research is a comparison of a couple different buildings, one that's built to a lower design standard and one that's built to a higher design standard. So they can be in the same location, have the same appearance, but one of them will have a lower initial cost and have worse energy performance and worse hazard resistance. The other will have a higher initial cost but have better energy performance and better hazard resistance. So what's really lacking in these comparisons is quantitative information on the economic and environmental benefits of sustainable and resilient construction. So what we essentially what we want to talk about is what is it that you get back from that higher initial investment, right? So, or like a payback period. Now, people are used to thinking about payback periods, right, where you have some kind of higher initial cost and lower operating costs. And this is showing an example from the use of solar panels, right? And what's a payback period for solar panels, right? You make an initial investment in your solar panels, and then you essentially have zero energy costs, or maybe not zero, but in some cases you can be earning money, and as a consequence you're able to determine what the payback period is and then what your savings are over time. So people are used to thinking about that when it comes to things that have this higher operating cost, like electronics or utilities, but what people aren't used to talking about that is in the context of buildings, particularly when it comes to topics like hazard resistance. So what I'm going to be talking about today is the way that we've been applying buildings to life cycle cost analysis, or applying life cycle cost analysis to buildings, and I just want to make sure that people understand the concept. You're probably familiar with it, but it's basically a method for evaluating the total cost of ownership. And what we want to do, usually we're comparing two alternatives, and we want to be able to combine initial construction costs with an operational costs that happen throughout the lifetime. And in this case, what you can say is alternative A is higher initial costs but has lower operating costs in the future. And when you sum up the net present value of those costs, you get that A has lower total life cycle costs. So that's important. What we've done is we've taken an approach to incorporate quantitative hazard resistance into life cycle cost, and we combine several different factors that you would expect in life cycle costs. One is the initial construction costs of constructing the building, and then the second is energy consumption. The third is like normal wear and tear, doing painting, replacing windows, things like that. And of course, we account for costs related to any demolition and recycling end of life. But a different element is this hazard repair. And what this does is it combines the probability that a hazard will occur with damage from that hazard. So let me talk a little bit about how we calculate those hazard repair costs. Essentially what we do is we combine data on the probability that hazards will occur. So this is the type of thing that you can get from government data. And what we do is basically get information on, for a particular hazard intensity, like let's say for a particular type of earthquake or hurricane, what's the probability that will occur. And we combine that with fragility curves for a specific building. Now, the fragility curves basically says for a given hazard intensity, what's the probability of having minor, moderate, major, or severe damage? So for, say a particular hurricane, we have a low probability of severe damage, a moderate probability of major damage, and then a significant probability of minor damage. So we combine both of those, and then for an analysis period, then across the whole analysis period, say 30 years, 50 years, whatever you want to define, we can then say over that time we have this amount of probability of minor, moderate, major, or severe damage, and we can associate exactly what kind of damage occurs over that whole time period, and then associate costs with that. And then what we can do is use that to quantify the life cycle costs over time. And what we include here is basically for a couple different design alternatives. One will have a lower initial cost, and the other will have higher initial costs. But then we take these costs here with the hazard costs and then spread them out over the building lifetime. And what you can see is that then you're able to calculate a payback period associated with that. So we've applied that life cycle cost analysis approach to a couple different cases for a two-story wood frame building in 3 different locations: San Francisco, where they have earthquakes; New Orleans, where they have hurricanes; and Charleston, where unfortunately they have both. And we look at 2 different building designs. One is a conventional design, and the other is a more enhanced design. And by enhanced, all I really mean is that there were some measures that were taken to mitigate against the effects of the hazard in that location. And sometimes it's just about changing your roof connection to the walls, or making use of shutters, and pretty minor things like that. We're not talking about like major structural changes or anything like that. So what are some things that we notice when we look at the net present value of these life cycle costs? You can see red is the initial costs, and they're pretty significant across all these cases. This orange is energy, blue is typical maintenance, and green is more substantial renovations. But what's in yellow and purple are basically costs associated with the hazard repairs due to either earthquakes or hurricane over this analysis period. And what's a little bit trickier to see, well, so first of all, in the enhanced designs, the initial costs are higher than the conventional across all the designs. What's interesting here is that the earthquake hazard repair costs are quite small. You can't even really see them in the Charleston case, and even in the San Francisco, they're barely visible. And that's due to a couple things. One is just the low probability that earthquakes will occur, and 2 is also the fact that we're talking about a 2-story residential building where you likely wouldn't get as much damage as, say, in a larger commercial type structure, where I'd expect this picture would be different. But what you can see here is that when we talk about hazard repairs due to hurricanes, those are much more significant. And in fact, for the conventional design in New Orleans, we calculate that you would spend more on repairs due to hazards from hurricanes over its lifetime than you would on the initial costs, right? So clearly you get, for that initial investment right here that's a little bit higher in the enhanced, you get significant benefit by having lower repairs due to hazards, right? So what we can do with that is we can take that and then put it into a payback period space. And so here we're looking at the cumulative life cycle net present value in thousands of dollars. And here we have the blue line is the conventional design, the red is the enhanced. And in San Francisco, those lines never cross over time, so there isn't a payback. But what we can see in Charleston and New Orleans, there is a payback of 2 to 5 years, depending on the case there. So pretty easy to make that payback over time in these particular cases. So what we learned from this is that life cycle perspective is really important, and then you can also have a reasonable payback for hazard mitigation measures. What we wanted to do, though, was to also look at what do we do in cases where we don't have data on the costs associated with hazard mitigation. So we had this question about basically how much should be invested in hazard resistance to break even across the life cycle. And let's say we had a couple of different designs here, and they had a different initial cost. But our real question is for design B, which has a more enhanced design against hazard to help with hazard mitigation. It will have much lower hazard costs associated with repairs due to hazards. And as a consequence, that's why it has a lower number right here. But what we wanted to be able to talk about is basically that means that there's an amount that you can spend on mitigation in this in order to break even across that whole life cycle. So in this case, you could spend another 14.3% in order to have this reduction right here, because sometimes it's basically easier to estimate what these numbers are rather than how much you would spend on that mitigation. So another way to stack it up is to basically say this design has this amount of hazard repair costs compared to this one, and we know what the initial cost of this design A, so we can do it in the context of design A and say that this is the amount we could spend on mitigation to break even. If we can do it less than that, then that's better. We can break even before the end of the whole period. But we just take that fraction and just call that the break even mitigation percent. So in the cases where basically you want to have like a rough estimate on how much you can invest and still break even over the building's life cycle, this is, we think, is a useful metric to kind of play with that early on in your thinking about the design process rather than getting into a lot of details on what hazard costs should be. So what we decided to do with that is analyze the break-even mitigation percent for a range of different designs and locations for wind hazards. So what we did is we took a Department of Energy reference building for mid-rise apartments, and so it has 32 apartments in it. It's about 34,000 square feet. And what we did is we looked at baseline and enhanced designs in wood, masonry, and concrete, which are the most commonly used design strategies for this type of building. And what we did is we analyzed the use of those in all counties in 18 eastern and Gulf wind-prone states. So we are looking at this specifically for wind hazards, so that's why we looked in this region. And across all analyses, what we did is we assumed a 7% discount rate over a 50-year time period. And as I said, what we want to do is basically see how this BEMP varies across all those different locations. So in order for us to do this, that's a lot of different regions and a lot of different designs, so we needed a more streamlined way to be able to analyze this. And so what we did is we took some standard building designs in a FEMA-issued tool called HAZIS, and then we also took data on wind maps for those different regions from ASCE 7-10. And what we do is we take both of those and then we calculate hazard costs for both conventional and enhanced building designs, and we do that using the FEMA benefit cost analysis tool. So all this data on the building designs and what they consider to be conventional, what they consider to be enhanced comes directly from those sources. And then what we do is we calculate those costs for those different designs for a few counties in all the states. So we have to do it a couple dozen times, but then what we can do is from that data, we can then create what we call a meta model by doing a regression analysis on all of the data that we've analyzed here. And then what we can do is then very quickly calculate this break-even mitigation percent for all the building types, for the mitigation mechanisms, and then for all of the counties. So this Streamlined tool allows us to analyze all those things very efficiently. And what it allows us to do is to look at different building scenarios. One thing we can do is look at different building scenarios in a single region. And what I'm showing here is basically all these, the table in, all the cells in this table will have numbers that show us what the BEMP would be from shifting, say, from a baseline wood design to maybe, you know, an enhanced wood design, or a baseline wood design to an enhanced masonry design. And we can do that for all these. We can either talk about a baseline wood design to a different baseline material, or a baseline to an enhanced. We can also look at going from some enhanced designs to another enhanced designs, but we assume we would never go from an enhanced design to a baseline design. So these cells are blank. But let me show you what this looks like for a particular region. So here's one value, so I don't overwhelm you yet, but this is for the region of West Palm Beach, and it's showing what would happen if you went from a baseline wood to an enhanced concrete. So the BEMP is 14.6%. And what does that mean? It means that we have, say, an initial cost for this building of $8.5 million, and we calculate in that baseline design that our expected hazard cost would be $1.31 million. If we start out with that same investment here, and we know that for this design we'd only spend you know, $60,000 on hazard mitigation based on the data that we have, that means there's an additional $1.25 million that we can spend on mitigation in order to break even across the lifetime of the building. So that's what that means for this region. And then when we fully populate in all these numbers, then you can see what all the transitions look like. So let's dive into each of these areas a little bit. What you can see here is that obviously these cells on the diagonal are just blank because you're not really doing a shift. But you can see a shift from, you know, say wood to masonry or wood to concrete. You can also see going from masonry to wood. A negative number means that you wouldn't ever recuperate your costs, so it wouldn't make sense to do that kind of shift. There's all sorts of positive numbers in this one right here, whereas these are all pretty low and even a few negative. So what do we take from that? Basically, what we see is that shifts to masonry and concrete within the space, they have positive numbers, so they're all beneficial. We see that in this space, all shifts are beneficial. So no matter what baseline design you're starting with, if you shift to an enhanced design using that same material strategy or even different ones, all the shifts are beneficial. Down here, what's interesting is that this says that all the enhanced designs perform pretty well. So, you know, like even like going from an enhanced wood to an enhanced concrete, only about 0.8%, you know, we'd call that about a tie. And so similarly, you got maybe a little bit of advantages going from an enhanced masonry to enhanced wood, this 2.4%, but not a big one. So what that says is that basically all the enhanced designs really do perform well. So that's just for one location. That's Miami Dade County, and we chose that one because it's one of the more extremes where you get some really high numbers. The other thing we can do is just look at one building scenario. So this is one of that extremes that we saw going from baseline wood to enhanced concrete, and this shows what the values are across all of the counties, right? And on this particular chart, we don't have any of these orangish, reddish colors, which would be negative numbers. But as you'll see, there are ones where that's the case. So we've generated these basically for all of the cells that are in this table. I'll only show you a couple here. But basically what you see is that, you know, as you'd expect, there are some of the darker colors are particularly in the southeast and along the Gulf Coast, and they go up to about the 20%. If we look at a different case, this is moving from baseline concrete to enhanced masonry. And so back on our chart, baseline concrete to enhanced masonry is right about in here. So this was Miami-Dade, California, where there was a positive number. And that's what's down here, but you can see it's a pretty low positive number, whereas what it says is that, you know, in a lot of these other places, it's a kind of orangish color, so it's a negative number. So about a tie there depending on the region. But the key message here is that this can vary significantly depending on which building scenario that you're looking at, and then also which region of the country that you're looking at. And fortunately, we have a tool that's available online, and if you follow up, we can provide a link, or I think this is actually something that Anne's going to post pretty soon. But it's a tool that you can use to basically explore which states you're interested in, or even which particular cities or counties. And then for that particular one, it'll tell you what's the average BEMP in that area, and then what are some of the particular costs, so you can explore those types of things. So just in wrapping up, what are some of our key takeaways? When it came to the life cycle cost analyses that we did, we saw that the hazard repair costs can exceed the initial costs. We also saw that investing in hazard mitigation can pay off in the long term. When it came to that break-even mitigation percent, we saw numbers that in some locations can be as high as 20%. That means that when you take a baseline design value, you can invest up to as much as an additional 20% over that and still break even over the lifetime of the building. But as we saw, the values really depend on what are the design scenarios you're looking at, and then what's the location. The other thing we saw is that the enhanced designs for all material types really do well at mitigating against the impacts from a hurricane. So quantitatively, I think those are encouraging. What we find, though, in talking about this with other people is that, we don't really quite have that culture of resilience that we'd like to have. We really think that we should be more proactive instead of reactive, and we saw that in the way that FEMA, or our even if it's not FEMA, but the way that our society kind of invests in hazard mitigation, that it usually happens a lot more after hazards than before. And I think part of this is that, when you talk to people about resilience, they don't really know what it means. They don't really have a way of understanding that. And so I think part of what we're just trying to do with this is to, start with education, to let people know, there is this way that you can invest in these things up front and then have payback later on. So we have additional information on our website, and of course you can always follow up with us with additional questions over email. But right now I'd be glad to answer any questions that people might have. And as we mentioned, we got some questions, or you can use the chat window, or let Anne know you're interested in asking a question.
Great. And so we do have one question.
Okay.
All right. So how do you address the challenge that original builder may not own the building for its whole life cycle, and therefore will not bear the cost of potential hazards?
Yeah, this is a really good point, and I think something that speaks to, that this goes beyond just kind of thinking about life cycle costs, but also, who bears the brunt of those. And so I think that one option is to try, when we quantify these things, is to try to get it incorporated more associated with the resale value of the house. And so that basically the person that's making, or I shouldn't say just house, but any building, right? The person that's making that investment sees that benefit, and obviously quantifying that in a market for real estate can be tricky. But another idea that we'd like to explore more, and have been trying to, is to see what are differences in insurance premiums for buildings that have different types of investments, like in hazard mitigation. And so we haven't quite been able to get the data that we're interested in to be able to do that. But I think that's how you do it, is to try to get it calculated more explicitly so that it can be incorporated into real estate value, and then also make it more explicit about how this affects insurance premiums as well.
Great, thank you.
Sure.
We did just receive the one question, but if anyone else has questions, either the chat or Q&A window are at the top of your screen.
Sure. It looks like, did Catherine flag herself for a question in there?
That was Catherine's question.
Oh, it was her question. Okay,
yeah.
good.
Yeah.
I see. Any others? We got some time, so. All right.
Okay.
Well, if no one else, then like I said, you can follow up by checking out information on our website or send us an email at cshub@mit.edu, and we'd be glad to follow up.
Thank you.
Okay. Thank you. Okay. Bye-bye.